All right, so we will come back to our line search algorithm with inexact step length computation. So recall that suppose we are doing steepest descent. Okay. So my direction is going to be the negative of the gradient of the function at the current point, and then alpha is going to be something that we will have to search for, and then the next point is going to be just xk plus alpha times s, and this is repeated until we converge. And last time we looked at some of the conditions which enable a reasonable alpha to be picked. So we looked at Wolf Powell conditions for an allowable alpha. So we said that if I'm able to, by hit and trial, able to find an alpha which satisfies two conditions that we listed last time, then that is good enough, and we can move, and the method will still be globally convergent with linear rate of convergence. So we also mentioned in passing towards the end of the previous lecture that this search involves bracketing, sectioning, and some interpolation. In the bracketing phase, we would like to find out the range in which I have to search for a good alpha. So looking at the picture, so currently I am at alpha equal to 0, and I need to search somewhere for alpha. So in what region would I search? So that identification of region for search is called bracketing. Once we have a bracket, then we only have to search within that bracket, and there is a guarantee that we will find the desirable point there. Sectioning is the part where once a bracket has been created, we narrow it down to get better and better points. And interpolation means that once I have explored a few alpha values, then I can try to fit a quadratic or a cubic to the given data and try to optimize over that. Okay, so today we would like to talk about a scheme which is almost like sectioning. It is called golden section search. This is a search procedure for 1D case, and that means it can be used for line search as well, because in line search we are searching along a single line in one dimension. It doesn't need derivatives. So that means it is easy to implement, but at the same time it might be slower than other methods, but it is quite simple to implement. It starts by picking up, so the input is given to us in this form of the limits that alpha can take. So so unlike this picture above where I don't know how far can alpha go, in golden section search I am given a range of alpha and I would like to find the best possible alpha from that range. So again a picture, alpha here. So somebody comes and tells me that you have to search for alpha between these 2 points only. You have to find the best possible value of alpha so that something is minimized, some function is minimized. So so the method is as follows. We start with 2 points. So we set alpha 1 equal to a, alpha 3 equal to b, and we pick 2 alphas and evaluate f at these 2 points. And then based on the value of the function at these 4 points, alpha 1, alpha 2, alpha 3 and alpha 4, we discard some region from our search and move on. Okay, so let's look at an example. So this is my alpha 1, this is my alpha 3. Let me pick some equispaced things here. So let this be, let me be consistent with the book. So this would be alpha 2 and this would be alpha 4. So we are free to pick alpha 2 and alpha 4. In the beginning, we may just take the middle values just to be safe. Once we have these 4 points, alpha 1, alpha 2, alpha 3 and alpha 4, we can try to make a plot, and this could be in various shapes and sizes. This is just one candidate. So so now the function values are denoted by these dots. So so what this method does is it chops off the least interesting part of the curve. So here, for example, we know that if there are 4 such values given to me, I don't know the shape in between. So we can chop off the least interesting part from the search over A and B. So which is this. So depending on the values. So I will compare this value and this value, and we should chop off the region which is closer to the higher value. So we can eliminate this region and try to search in between here. So again, I don't know the shape of the function, so this one is smaller, this one is larger, so I'm going to chop off this region and say that there has to be some locally optimal solution in this part, and then do this whole exercise again. So now, starting with these 3 points, we pick a 4th point once again. Let's say its value is this, and now out of the 2 middle points, this one is better, so I'm going to chop off this region and continue so on and so forth. This doesn't really guarantee that I will reach a globally optimal solution, but it does guarantee that there would some locally optimal critical point we will be able to get. The important question here is how big should this be? So the answer is that once I chop off, I should get a symmetric figure. So first is these two lengths should be same, and the second condition is that suppose I'm chopping off this region, then I should be able to select a new point now somewhere, so that I get a nice look at other points. So in the next stage, I'm going to pick a point here and plot the function values, and then repeat this procedure again and again until my bracket size, this extreme shrinks to a very small acceptable length. So this is called golden section because this ratio. So the ratio from here to this, so this is 1:tau, where tau is the value of the golden ratio, which is 1 plus square root of 5/2, and this can be shown quite easily that if you use this tau, then you will steadily reduce the region, and it is fairly efficient. Okay, so where is this golden section search used? So it is used to find solutions for 1D problems. So you can use it as a subroutine for your steepest descent. The only catch here is that I really don't know the endpoint, and either I make an intelligent guess or arbitrarily pick, based on experience, this endpoint. But once this last endpoint is known, all other points are easily known. So why should this tau be this golden value? Well, it turns out that if you pick this tau, then you chop off the maximum region consistently. In other schemes, you can pick it to be other value, but then sometimes you might cut off a small piece, sometimes you might cut off a larger piece. So this is a fairly good method to be used, especially since it is simple to implement. The downside is that sometimes you might have to evaluate the function at many more points than necessary, but that is okay. So that brings us to the close of chapter 2. We have rushed through most of the theorems and lemmas and their proofs. I request you to read them at least once and try to get the gist of why those things are true. And in the next lecture, we will be starting chapter 3 of Roger Fletcher's book, which is about quasi-Newton methods and Newton method. So with that, I will stop. See you next time.